All right, so this is a lesson reviewing key aspects of exponential functions, and I'll start with review of exponent laws. For example, if you're multiplying two powers with the same base, you add your exponent, so I can summarize this as x to the power of a plus b. If you're dividing powers with the same base, you can subtract the exponents, so you have x to the power of a minus b. If you're multiplying, if you have one power raised to another power, you can write that as the base raised to the two exponents being multiplied to each other, so a times b. If you have multiple factors all being raised to a power, you can write each of those factors individually to that same power. Helps if I pay attention to the variables. Here we go. And same thing, if I'm dividing factors, if I have a rational expression raised to a power, if I want, I can write it as each the numerator and the denominator to that power. And remember, before I get to the next line, that it's really easy. I find a lot of students tend to look at this one way, like you go from there to there, but of course, we can go either way. Right? If these are true, I should be able to look at these in either way. Down here, a power of 0 equals 1. Essentially, a power of 0 you can think as meaning the base divided by itself. That's a perfectly valid way of thinking about what a power of 0 means, that base divided by itself. So the only exception to this is as long as x is not 0. If x is 0, then you have 0 divided by 0, which is undefined. So x to the power of 0 is still undefined, not 0. X to the negative a, well, positive exponents mean repeated multiplication, so negative exponents mean repeated division. So x to the negative a is the same as dividing by x a times. And so in practice, when we deal with negative exponents, we tend to see all these reciprocals. And so when you have a negative exponent in the denominator, that means you're repeatedly dividing, but you're also still dividing. And so you're dividing by dividing, which is the same as multiplying. I probably just made that sound more complex than it really is. But in practice, when you have a negative exponent in the numerator, same as a positive exponent in the denominator. And if you have a negative exponent in the denominator, same as a positive exponent in the numerator. All right, so when you have a rational expression to a negative exponent, you can always rewrite this as the reciprocal. So instead of x over y to the negative a, I can write it as y over x to the positive a. And lastly, when I have a rational exponent, like a fraction of my exponent that involves radicals, so I can think of this as either the bth root of x all to the power of a. I can think of it like this, or if I want, it's completely equivalent. I can think of it as x to the power of a, and then the bth root of all of this. Perfectly equivalent. And that reviews our work with exponent laws going mostly grades 9 and 10. All right, so an important part of Pre-Calc 12 was understanding exponential functions. And hopefully you remember there's two basic types of exponential functions. And by definition, an exponential function is any function in which your base is a constant and the variable is the exponent. But the base can't be any number. It has to be a positive number that's not 1. And so assuming you have an exponential function, there's two types. And it depends if your base is more than 1, like the one on the left, or the base is between 0 and 1, like the one on the right. So if you have a base that's more than 1, it's an example of exponential growth. And now so it looks something like this. Crosses the y-intercept at 1, has a horizontal asymptote on the x-axis. And again, that's what exponential growth looks like. And if you have a base between 0 and 1, it's exponential decay. Still has a horizontal asymptote on the x-axis. Still has a y-intercept of 1. It's just going the other way. And again, algebraically, I can show you how these two must be horizontal reflections of one another. If we think back to about what negative exponents mean, for example, if I look right here at 1/2 to the power of x, that's the same as 2 to the negative 1 to the power of x, right? Because 2 to the negative 1 means 1 divided by 2. And again, we have a power raised to another power. You multiply your exponents, so the same as 2 to the negative x. Which again, I can now see algebraically that 2 to the power of x and 1/2 to the power of x must be horizontal reflections of one another. All right, let's look at a typical kind of exponential question involving compound interest. And so I have a couple examples here that are almost identical, They both start with a $5,000 investment. It grows at 8% annually. But the first example, it's compounded annually, which means every year you get 8% of the previous year's value all in one step. And we want to write an expression that shows what this is worth after 18 years. And so if you have compound interest or something's compounded annually, like I said, it means every year in this case you get exactly 8%. And so an expression for after 18 years, you have your initial amount, 5,000, times 1 plus 0.8. And again, yes, this is the same as 1.08, but I like writing it like this because it makes it more clear, well, how the next one's going to look. But essentially, if you're adding 8% to something, that means you're having 100% of what you started with plus an extra 8%. And that's 108%, which written as a decimal is 1.08. Because remember, 108% literally means 108 divided by 100. That's all that percent symbol literally just means divide by 100. And 108 divided by 100 is 1.08, right? These are all equivalent. That's it. That's my little grade 8 math portion of the lesson. And if this is compounded annually, that means literally every single year you get this extra 8%, 8. So it's for 18 times. Now if you actually go, that's the expression. I'm done the question. That's it. If you go to a calculator, after 18 years, this is worth about $19,980.10 if we round to the nearest cent. Okay, so what if I have still the exact same setup, but it's compounded monthly? Well, in this case, that means every month you don't get 8%. Every month you get 1/12 of 8%. But it happens every month. So the equation is very similar. 5,000 times 1 plus, not 8. Now, every time this grows, it doesn't grow by 8%. Like I said, it grows by 8% divided by 12, 1/12 of 8%. And so in 18 years, we don't add this amount, right? Because this factor here is the amount of percent we're adding each month. In 18 years, it doesn't happen 18 times. It happens 12 times 18 times. 12 months times 18 years. And that's the expression. That's the most important part to me. That's it. Notice if I actually do evaluate this on a calculator, I get $21,002.87. So notice, if I compare these two, and hopefully you already remember this about compound interest, if I have the exact same interest rate, exact same time frame, exact same initial amount, but I'm compounding more often, it grows a little bit faster. You know, in 18 years, this one below is a little more than $1,000 more. So it is a noticeable difference, but that is over 18 years. And so the idea then is if I can figure out how to compound it monthly, I could compound it daily. If I was compounding it daily, you know, this 12 would be 365 because every day you get 1/365th of 8%. But it happens 365 times a year, ignoring leap years. And I could make any sort of compounding periods. I'm going to go back to here. So with that said, yes, the more compounding periods, the more often we compound, the faster it grows, but it's diminishing returns. It's not like if I compound it weekly, I'm now going to get, you know, another $1,000. If I compound it daily, it's going to be another $1,000 after that. After, you know, the more and more we compound, it does go up more, but by less and less. Which means that leads to this sort of weird abstract idea, which is something compounding continuously. If something compounds continuously, the idea is by compounding periods, you know, 12 times a year in this case, it gets closer and closer to infinity. It gets infinitely large. So imagine this approaching infinity. So I'm, you know, every second, every millisecond, every millionth of a millisecond, we keep having more and more compounding periods, but this also then is approaching infinity. So what happens? Well, that idea of this actually approaching infinity, which means every instant, which means not 0 time, but infinitely close to 0 time, we have a new compounding period. And every instant we get an infinitesimally small amount of extra interest added. Not 0, infinitely close to 0. And so it's a weird idea, but what that really means, what it looks like, is if you have something compounding yearly, you have these steps. If it's compounding monthly, you just have more steps, closer and closer to each other. If it's compounding continuously, it is continuous. There are no steps. It's a continuous curve. And so while it sounds kind of strange, this idea of something growing continuously, it's actually the easiest to visualize. If I wanted to show some sort of growth of anything, If something's growing continuously, I just draw a curve. If it's growing exponentially, it looks like that, as opposed to these steps, which is actually what, something's compounding in any interval. It's a series of steps. So like I said, an example of something that sounds really abstract in many ways is, but is also visually pretty easy to show. It's just a continuous curve. There's no breaks, there's no steps. And while this doesn't have to apply to just money, that's a good starting point. And so we call this continuous growth or continuous decay. And if I have something that's growing continuously, and thinking back to money, that means it's compounding an infinitely many number of times. All right, then this equation here can model it. And so what do we have here? Well, A naught is the initial amount. So A naught is some initial amount. It could be money. It could be, again, anything that we're choosing to model this way. R is the rate of growth or decay. And T is the time frame, which again depends, the units of time depend on the rate. Because a rate of growth should always have some sort of time frame attached to it. For example, my previous examples here, we had 8% annual interest. So that means per year. And so the time frame would be in years. But there's no rule saying percents have to be per year. But if you understand your growth rate, there should be some sort of time frame to it. And again, E is Euler's constant. E is approximately 2.718, but it's exactly E. So we don't really ever use 2.718. It's approximately that, but again, it's exactly E. So exact same setup, but now we have something that's compounding continuously. Which means, in some ways you can look at it like this. That means we have $5,000, 1 plus 8%, that's 80%. Divided by, now I can't put infinity, because infinity is not actually a number, but I could do this. I'm going to put just an x. Actually, no, I'll put an n, because usually we put n for number of compounding periods. And then up here, I'm going to say it's n times 18. But this n, which I'm going to highlight in a lovely pink color, this n is approaching infinity, and we want to think about what happens as n gets infinitely large. So I'm going to write something down that, honestly, right now I don't care if it makes sense to you or not, because it's really introducing something that we see in the next unit, but it can't hurt to write right down. I'm going to say I want to write here the LIM, which is the limit as n approaches infinity. So that's what we're really doing here. The idea is what happens as n gets infinitely large. Now this little notation of LIM for limit, that's really what we start looking at in the second unit of this course, which is called limits. But essentially what this means right now is, okay, I can't actually substitute infinity into an equation. Infinity is not a number. But I get the idea that as n gets larger and larger and larger, this total value doesn't get infinitely large. It kind of, like I said, the more and more you compound, it gets more, but less and less so. And so that said, this here, which sounds kind of strange, because how do you evaluate this when n, you can't actually put infinity in? Well, this is always going to be the same as 5,000 times e to the power of r, which is 8%. Again, not 80%, 8%, times t, which is 12. So while I can't directly evaluate this expression at the top, I can directly evaluate this expression right here. And if you type this into your calculator, I get about $21,103.48. And that is compounding continuously. So notice if I compare this to, if I look at my three examples, compounding yearly, $20 shy of $20,000. Compounding monthly, it's $21,000, extra $1,000. When it went from one compounding period a year to 12, when I go from 12 to infinity, notice how much extra money I made. I made an extra $100. Okay, so like I said, the more you compound, the more often we have these compounding periods. It does increase, but it less and less so, and you can't compound more than this. This is infinitely so. And so with that said, kind of an abstract idea, but like I said, if we were to visualize the graphs over 18 years, this would have 18 steps slowly getting higher and higher and higher. This would have 12 times 18 steps, slowly getting higher and higher and higher. This would be a continuous curve. There'd be no breaks. I know which one for me was the easiest to draw. Okay, an abstract idea, like I keep saying, but don't miss the simplicity of it in some ways. This is just a curve, a continuous curve with no breaks. So the last question has to do again with a regression equation that I've just found for you. So what I have here is the data for the minimum wage in British Columbia from 1965 to 2018. And you can see here a scatter plot. The green points are is the data, where I've set up my x-axis as years from 2000, just because it's kind of a nice number to deal with. And the y-axis is the minimum wage in those years. These are the years that minimum wage changed. So I will say, while this is a scatter plot, the data, in many ways, these are actually all, minimum wage was kind of constant in between. So when you see a longer break, you can see minimum wage was constant for a really long time in the early 2000s. And then it's been changing a little bit each year recently. That's it. I put that information into Desmos, and it came up with this regression equation here. And it's a continuous growth equation, and that's what you see sketched in black. Or not sketched, that's what Desmos drew in black. So W representing the minimum wage, T years from 2000. All right, so with that said, notice it's not a perfect model, but it's pretty good. I mean, and honestly, we're modeling something that's pretty complex, like when minimum wage has to do with inflation. As things get more expensive, they have to raise wages, but it also has to do with politics. Some parties are more keen to raise wages than others. I mean, there's a whole bunch of things that come into play here. So yeah, it's not a perfect model, but it's not bad. And I want to now work with a model. So my first question is, what do these coefficients of 6.75 and 0.33 represent in this context? All right, well, let me write down the equation again right here. So we had W equals 6.75 times e to the 0.033t. Well, let's compare this to that general form I had for continual growth. A equals A naught times e to the 0.033t. Oh, sorry, not 0.33, RT. So I can see 6.75 is the initial amount, and I can see 0.033 is the rate of growth. Well, in this context, what is the initial amount? Well, that is the minimum wage in year 0. What's year 0? 2000. So 6.75 is the minimum wage in the year 2000 according to our model, right? So 6.75, the coefficient, represents the minimum wage in BC. In 2000. So 6.75 per hour, okay, according to the model. Let's say the regression model. Because yes, if we look in the actual data, the year 2000, well, actually, well, right there, it was probably a little more than $7 an hour. But again, it's just according to the model, right? 0.33, that represents the rate of growth of minimum wage. So in this case, 3.3% per year continuous growth, and which is related to inflation. But again, there's other things in it as well. Again, minimum wage is tied to a whole bunch of parameters here. So the 0.033 represents the rate of growth of minimum wage. Or I should say, and really, I probably should say like the average rate of growth, like on average each year. But I'll say rate of growth of the minimum wage in BC. And so in this case, it's growing on average by about 3.3% per year. Like I said, a rate of growth has to have some sort of time frame. And again, according to the model. But even though the model is not perfect, what that tells me is that, roughly on average, minimum wage over the last, what is this, 50-ish years has been growing, about 3%, a little more than 3% a year. All right, so now let's use the model for 2 questions. Use the model to predict the minimum wage in the year 2040. So for this, the year 2040, that means I want t to equal 40 in my equation because t represents years from 2000. And so I'll say w of t equals just my equation. And that's it. And you go to your calculator, should get about 25.27, which represents $25.27 per hour. That's the model. That's the prediction. In year 2040, minimum wage would be about $25 an hour in BC, which again could sound ridiculous, but like I believe I mentioned before, you know, when I was in high school, minimum wage was $4 an hour. And so the idea of minimum wage being about $15 an hour now, when I was a teenager, would have sounded ridiculous as well. So I mean, it is a prediction. I'm not going to say this is going to happen, but I can't just say that sounds way too high. And then the other way around, use the model to predict in which year minimum wage will be $20 an hour. So for this, I know the output is 20. I want to solve for t. So how do I do that? Well, first, let's divide both sides by 6.75. Okay, and here's the main thing. What do I do next? Well, I have to somehow use logarithms, and there's many ways. But yeah, I have to use logarithms in some way. My general recommendation, right here I have an equation in exponential form. Any equation in exponential form you can write in logarithmic form. That's it. There's lots of ways of thinking about this. It's all the same in the end. So in logarithmic form, this looks like log base e, because e is the base of the exponential expression, of the input of my logarithm, which should be the output of my exponential equation, so 20 over 6.75, and this will equal what was the input of my exponential expression. And other ways of looking at this is to log both sides. And again, there's various ways. In the end, it's all the same. That's it. Log base e, I'm hoping we remember, is the same as the natural logarithm. So these are equivalent. And hopefully soon and later we can actually skip this step right here and go straight from here to here. It all depends how familiar you are with the natural logarithm, which for this course is by far the most pleasant and important logarithm there is. That's it. That means I can now see t will equal, before I go to my calculator, the ln, or the natural logarithm of 20 divided by 6.75 all over 0.033. And that's it. I haven't actually calculated this in advance. Let me see what this is. So I get about 32.9, so roughly 33. So that means 33 years from 2020. Sorry, not 2020, from 2000. So the year, approximately year 2033. So according to our model, in the year 2033, minimum wage in BC will be $20 an hour. And again, it is just a prediction, but it's a prediction that's it's an educated guess. It's not just a guess. So lastly, notice right at the very end, we have to start using logarithms. I haven't really reviewed logarithms with you yet. Hey, that's what comes next. All right, and I'm going to